Hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the concept of orbital diagrams and the electronic configuration. And this is going to be basically some of the examples that we're going to do using specific elements. Now, in our last discussion, I had basically mentioned that the concept of orbital diagrams are going to show arrangement of electrons in an atom. And of course, this is going to be given in terms of each specific orbital being occupied by a particular number of electrons. Now, given a specific rules which we must follow in order for us to make this specific orbital diagram. And these are the Aufbau's principle, which basically is sometimes referred to as the builder principle. And given a specific set of course, numbers, arrangement of numbers, which was going to assist us in trying to describe the sub-levels in terms of their energies. And then I've spoken about the concept of the Hans rule. And this Hans rule is going to dictate on the orbitals of equal energies, which are going to be contained in this specific case. And they are given a specific example of the p orbital, which is going to be given as a set of three orbitals. Now, in this case, orbitals of equal energies are referred to as degenerate orbitals, whereby we're going to see that the arrangement of electrons in these particular orbitals are going to be given in a particular order. Now, according to Hans' rule, before we begin pairing up of this specific electron, we had said that each of these orbitals is going to consist of a maximum of 2 electrons. So therefore, for us to fill these specific orbitals, perhaps for this is a p orbital for x, y, and z, we're going to distribute these electrons in a way that they're going to singly occupy each orbital before they begin this concept of pairing up. So this is going to be according to the Hans rule. And lastly, I mentioned the concept of Pauli's exclusion principle, which of course emphasized on the concept of spinning of electrons or orientation of electrons in opposite direction. So for this px orbital which I've basically written this or given a designation for these electrons using the opposite direction for this arrow. Now this is going to indicate the opposite spin. So according to Pauli's exclusion principle, if these two electrons are going to be occupying the same orbital, they are going to be given in terms of the opposite spins given as such. So these are some of the rules which are applicable in trying to give an electronic configuration for, or rather the orbital diagram for a specific element. Now in this case, I'm going to give an example of oxygen of atomic number 8 given as such. Now, according to the Aufbau's principle, given different, of course, the levels of energies of various subshells, whereby we say that we can represent this one using this specific, perhaps I can just give it in summary form. So I decided that we're going to have this particular arrangement of numbers, which is going to describe various subshells and their particular energies given in this specific order. So we're going to have the first column for the S, and then we shall have the second one for the P, then we shall have the third one for D, and then lastly we shall have this one for F given as such. So we shall have D, P subshells, and then we shall have the first one as S subshell given as such. So according to the Aufbau's principle, this is going to be building up using these specific arrows. So the direction of these arrows is going to indicate an increase in the number of energy for these various subshells, and therefore we're going to use this specific trend in trying to give a specific arrangement for electrons of various elements. Now they are going to go in this specific order in a sense that this is going to follow this specific order, whereby we're going to have the 1s orbital having the lowest energy, and then followed by the 2s orbitals, 2p, and then we shall have a 3s orbital, and then we shall have a 3p orbital, going in that particular order. So for oxygen, we're going to have this electronic configuration given in terms of 8 electrons. This is the atomic number. So we're going to have this one given in terms of 1s, and then we shall have 2s. So as we said, each orbital is going to contain a maximum of 2 electrons. So we shall have 1s for 2 electrons, and then 2p. So for an electron configuration that is containing 8 electrons, this p orbital is going to consist of a maximum of 6 electrons. So we're going to have this one having 4 electrons given as such. So this specific arrangement that I've given on the board for an atom of oxygen with atomic number 8 is going to be referred to as the electronic configuration. Now in this case, if we try to look at this according to the, of course, the spin or the principle which I've mentioned for, of course, Pauli's exclusion principle, this is going to be giving us no information, especially concerning the spin or the orientation of these specific electrons. Now we can introduce another version of representing this specific arrangement by having this specific atom of oxygen represented using the 1s, 2s, and of course the 2p orbitals. Now this is going to consist of 3 degenerate orbitals given as such. So we shall have, so I'm going to arrange this one in terms of this one because of us, just in summary form. So we shall have those specific electrons occupying the orbitals given as such. So if we try to look at this, we shall, so therefore these electrons are going to occupy the p orbital, of course, singly before they start pairing up according to, of course, this Hans rule which I've mentioned in this specific discussion. So in a sense, we can represent this particular configuration for oxygen using this specific format. And then secondly, we're going to do this one using this first format which I mentioned. So the first format is referred to as electronic configuration, while the second format is going to give us what we refer to as an orbital diagram given as such. So in this particular case, we can have a version of a representation of these two specific, particularly the electron configuration in a shorthand form, by using the concept of the noble elements, which I'm going to particularly give on the board using an example of an element. So these noble elements are going to create for us a summary for trying to represent, or a shorthand form in trying to represent electronic configurations of various atoms with many electrons. And of course, we're going to see that this is going to be handy in a sense that these noble gases are going to have their S and P orbitals being full, and therefore they can be able to assist us in representing the inner shells of our large atoms which I've mentioned. Now, for instance, if we have an example of an element like bromine, bromine has got an atomic number of 35. So we're going to look for a preceding noble element, which is going to be, of course, argon. So therefore, we're going to see that argon is going to consist of an atomic number of 18. So the difference between this argon and, of course, bromine is going to be 17 electrons. So therefore, for us to represent this specific element of bromine, we are going to have it represented as brackets, and therefore we're going to use the addition from that specific arrangement which are given in terms of an array of numbers. So therefore we are going to consider these specific orbitals, and these are going to be the 4s orbitals, which are going to consist of 2 electrons, the 3d, the 10 orbitals. The d orbital consists of 5, the d subshell consists of 5 orbitals, which are going to be occupied by 2 electrons each, and therefore a total of 10 given as such. And then we shall have the 5 and the 4p orbitals having 5 electrons. So in this particular case, then therefore we're going to see that this is going to be the specific arrangement. But in consideration of the specific orbitals which are going to be, of course, taking place, we can be able as well to represent this specific configuration in terms of what we refer to as valency configuration. And this is going to consist of valency orbitals, which basically are going to be represented by the s and p orbital. So therefore, from our representation of this shorthand notation using the noble gases, we can represent bromine using, of course, the noble, of course, the valency shells, which are the s and p. And therefore, this is going to be in terms of 4s2 and 4p5. Remember, this one is full. So therefore, we're going to represent this one, which are going to be the valency subshells which can be given in this specific format. And this specific arrangement, therefore, is going to be so this is going to be a shorthand form, or a shorthand format for representing these, of course, atoms with large number of electrons. And then we are going to have the valency configuration for representing these specific large atoms using this representation for S and P, of course excluding these specific orbitals. So in this case, we are going to look at various examples, and that's going to open for us a window in trying to describe other larger atoms. For instance, if I can give a lead. A lead can be given in terms of an electronic configuration using example of a xenon. And this is going to be given a square bracket as such. And then we can have a valency representation using the 6s2, of course, orbital, and this 6p2 given as such. So in this case, we're going to give various examples in other videos that are going to follow. Kindly check our description boxes for various links of other similar videos, and follow and subscribe to our channel for more. So that is it for now, guys. Bye, God bless you. Catch us in our next video.